question 2, part 2, we're asked to determine if the functions y1 is equal to e to the 2x sine of 5x and y2 is equal to e to the 2x cosine of 5x are linearly independent. So recall from your lectures, to determine if two functions are linearly independent, you need to use the so-called Wronskian test. The Wronskian test tells you that if the Wronskian of y1 and y2 is equal to 0, then the two functions are linearly dependent. If the Wronskian is always non-zero, then the functions are linearly independent. So to test if y1 and y2 are linearly independent, we need to construct the Wronskian. Again, recall from your lectures that the Wronskian of y1 and y2, which we call W, that's simply the determinant of the 2 by 2 matrix whose first row is y1, y2, and whose second row are the derivatives of y1 and y2, y1 prime, y2 prime. And then working out this 2 by 2 determinant, the Wronskian is equivalently equal to y1, y2 prime minus y2, y1 prime. So here we need to sub in y1 and y2 into this Wronskian. Before we do that, we're going to work out the two derivative terms, y1 prime and y2 prime. So looking at y1, we can see that if we need to differentiate y1, then we need to use the product rule and then also the chain. So y1 prime, well, using the product rule, that's going to be e to the 2x times the derivative of sine of 5x, which, according to the chain rule, is 5 cosine of 5x plus sine of 5x times the derivative of e to the 2x, which is 2e to the 2x. Next, multiplying all this out, well, we get 5e to the 2x times cosine of 5x plus 2e to the 2x sine of 5x. Now here we can factor out the common e to the 2x. So y1 prime is equal to e to the 2x times 5 cosine of 5x plus 2 sine of 5x. So now we've worked out y1 prime. y2 prime, it's the same procedure. To differentiate y2, use the product rule together with the chain rule. Working that out, you'll find that y2 prime is equal to e to the 2x times 2 cosine of 5x minus 5 sine 5x. So now we've worked out y1, y2 prime, so we can evaluate our Wronskian W. So, substituting our expressions for y1, y2, y1 prime and y2 prime into our equation for W, we find that the Wronskian becomes e to the 2x times sine of 5x, which is y1, times y2 prime. Well, recall previously y2 prime worked out as e to the 2x times 2 cosine of 5x minus 5 sine 5x. And that's going to be minus y1. Well, y1 was e to the 2x, sorry, y2, which was e to the 2x cosine 5x, and then times y1 prime. y1 prime was e to the 2x times 5 cosine 5x plus 2 sine of 5x. So all I've done here is just substituted my y1, y2, y1 prime, y2 prime into my earlier equation for the Wronskian. Now, all that remains is to just work all of this out. So, a little bit of messy algebra. So, if you multiply out the first term here, you'll get 2e to the power of 4x times cosine 5x times sine of 5x minus 5e to the 4x sine squared of 5x. So all I've done here is just multiply all of this first term out. Similarly, if you multiply out the second term, you'll get minus 5e to the power of 4x cosine squared 5x minus 2e to the power of 4x cosine of 5x sine of 5x. Like I said, just a little bit of messy algebra. But other than that, relatively straightforward. Now, if we inspect this expression a little closer, we can see that the first term, well, that's the negative of the fourth term. So the first term and the fourth term cancel each other out. And then we're just left with the second term and the third term. So writing those out explicitly, that's minus 5e to the power of 4x sine squared of 5x minus 5e to the 4x cosine squared of 5x. But notice here, there is a common factor in both terms, minus 5e to the 4x. So if we factorize out that minus 5e to the 4x, we're left with minus 5e to the 4x times sine squared of 5x plus cosine squared of 5x. But recall from your study of trigonometry, sine squared of 5x plus cosine squared of 5x, that has to be equal to 1. And of course, minus 5e to the 4x times 1 is minus 5e to the 4x. Now this expression here, that's always going to be non-zero. So this minus 5e to the 4x, that's non-zero for all x real. Well, in that case, the Wronskian, which is what we were calculating, is non-zero for all x. According to the Wronskian test, this would imply that y1 and y2 are linearly independent. So in this example, we've shown that the Wronskian of y1 and y2 is non-zero for all x real. And according to the Wronskian test, that would imply that y1 and y2 are linearly independent.